I welcome you all to the 5th keynote for the ICTer conference. Let me introduce the keynote speaker for the day, for this session. Professor Marcel Baunach is a professor for embedded automotive systems at the Institute for Technical Informatics at the Technical University of Graz, Austria. He received his doctorate in computer science with distinction from the University of Würzburg. He established the research area Wireless Sensor Actuator Networks with a focus on embedded operating systems, hardware platforms, wireless communication, and indoor localization. In 2011, he joined the industry as a department manager for hardware development in the field of automotive diagnostics. In 2013, he returned to the academic world and moved to Graz University of Technology. Professor Baunach is currently a member of the Extended Management Board of the Operating Systems Division. His field of research is the dynamic composition of hardware and software of embedded systems. In particular, the co-design of adaptive multi-core architectures, flexible operating systems, and self-organizing communication protocols for embedded real-time systems. Areas of applications include the Internet of Things, autonomous driving, and future production systems. He is always promoting young scientists and willing to support your academic and promote their outstanding work. One of his objectives is to strengthen the awareness of the need for strong research and teaching on operating systems and processor architectures. His keynote for today will be on dependable computing platforms for Internet of Things. Over to you, Professor.
Thank you very much for the kind introduction. Oh, something has happened to the slides. Wait. Now, it looks better. Okay, I hope you can hear me. Yeah, the Internet of Things. It has to be a dependable thing. And the reason for that is that the Internet of Things will simply be everywhere. By 2020, and that's not too far away, it's only 3 years, we will have about 50 billion connected devices to the Internet of Things. Is that okay? Um, 50 billion devices connected to the Internet of Things. And this is one of the facts why these IoT will be one out of the 10 most disruptive technologies for the next decade. Another reason for that is that the Internet of Things will definitely impact most critical areas of our daily life as we know it today. It will have a strong impact, for example, on smart cities, so the way in which we manage the cities. It will have a strong impact on energy, like power grids and power plants. How do we manage these? How do we distribute the energy across the country and within cities? It will have significant importance for water management and irrigation systems, for transportation in the air, on the water, and on the roads, and of course also for our communication. And in the end, it will be important as an infrastructure management concept. And the Internet of Things will itself become something like a global and highly critical super infrastructure for all the other infrastructures we currently have. So nowadays, we build infrastructures for different things, like the ones you can see in this list, smart cities and so on. But in the future, we will have this new infrastructure, the Internet of Things, beneath or below all those infrastructures, not only as a new base for them, but also connecting those infrastructures. And therefore, the Internet of Things must not fail. Once this base fails and it breaks down, then all the other infrastructures that will be built upon it will also break down and fail. And this is something we cannot accept. But this requirement is a true challenge, since the Internet of Things is unprecedented in a couple of aspects. First of all, the number of involved application domains. I already said so in the last list. You've seen a couple of infrastructures that are affected, but there are also application domains like automotive, space, medicine, and so on. They are involved in this Internet of Things. They will be affected. Another thing is that the distribution and the deployment of IoT devices will be immense. So you will have devices everywhere. Underwater, in forests, on the open sea, in the air, in buildings, private buildings, also non-private buildings, it will be everywhere. And those devices, 50 billion or even more, they will be extremely heterogeneous. You cannot expect to have 50 million identical devices somewhere. So if you know one, you know all of them, or if you update one of them, then automatically all the others update as well, but they will be different. And that makes a huge difference as well, because it becomes very difficult to maintain those devices in the future. Apart, over time, as time proceeds, of course, those devices will change. They will be adapted to new requirements, to new laws. They will be adapted because of bugs that have been found and were corrected. So the composition of the software and also of the hardware that can be found in these devices will be different as well, and will become different and even more different over time. And another thing that might not be that obvious is the vulnerability aspect. If you imagine that each and every single IoT device is connected to this huge network, to this huge global network, then imagine a hacker gets access to one of those devices. If the network is not protected properly, then the hacker can access the entire network through this single device. And since the devices will be deployed everywhere, so maybe even in this room, somewhere on the floor over there, it's very easy to access, to physically access this device. So we need to have strong protection mechanisms on a physical but also on a software base that prevents an attacker to enter the entire IoT. Then there is a need for long-term maintenance. Imagine you have deployed several devices for your special application somewhere, and after some time you find out, there's a bug. Or I've implemented an algorithm, it was okay at that time, but 2 years later I know I can do better. I can simply do better, and I want to install this new algorithm or this new application into the devices I have deployed years ago. Then you need to have proper maintenance concepts. Today it's more like an embedded system is designed, it's implemented and tested, and then it's deployed. And from the moment on, it's most commonly not modified. Yeah? Especially in the automotive domain, in medicine or in space technology, people avoid modification of existing systems. The reason is obvious. As soon as you modify something, you would have to retest it. Testing is expensive. Sometimes it's not even possible, especially if the device is deployed in a car that is moving around and you don't want to call that car back. So you cannot test, and thus you avoid the modification. But in the future, you have to update the devices. Since there will be new laws and your device has to respect the laws. Let's talk about car-to-car communication, for example. All the protocols we have today are not yet really standardized. There are some concepts that are widely accepted, but there are no real standards. Nevertheless, cars are already communicating. In the future, once we have regulations and standards for this communication, you have to update all the embedded devices that are already communicating today. Otherwise, those devices cannot participate in the network any longer, making them useless for the IoT or even disturbing the remaining IoT because of their old software and hardware. So the need for maintenance will become more and more important, just to reflect changing requirements. And therefore, we definitely need proper and very sustainable design concepts right from the beginning. So it's not a good idea to simply start by designing a device and another one and yet another one, but we have to have proper design rules for the design. Otherwise, we cannot cope with those challenges. So the IoT and each device in there has to be extremely flexible and, of course, dependable. And dependable is a term that is widely used nowadays. It means something like, the stuff works. But what does it mean in detail? It means that each device and the entire network performs according to the specification under any condition. So in order to provide that, we need to also provide guarantees on some aspects. First aspect is security. So we have to prevent an attacker, or we have to make sure that the device is not misused or altered in an uncontrolled way. This mainly affects integrity and confidentiality. Integrity means that all the data that is stored and processed in a device is not altered is not altered unexpectedly. Confidentiality means that whenever there is some data available on the device, no one can read out that data without authorization. Yeah? So this is a protection. The next thing is real-time capability. So the requirement is continuous, correct, and accurate and timely service at any time. Doesn't matter what's happening, the device responds according to the specification within a certain time frame. The third thing is safety. Safety means that even if there is some problem, let's say there is a bug or there is some external perturbation maybe, the system will never ever harm its environment, especially not humans that are working with the device. So expect or imagine you have a device in the medical area, everything works fine, and then due to some strange thing that happens, maybe you don't even know what has happened, the device acts in an undefined way, and in the end, a human is maybe even killed. This is totally unacceptable, so we have to make sure that the devices are safe and do not harm their environment. And the last thing is maintainability. This is what I already told. It's a requirement to be flexible to adaptations and updates. And of course, when we started to build, or when people started to build embedded systems, then mainly computer scientists and electrical engineers were involved. But we found out very quickly that this is simply not enough, since cooperation across scientific disciplines is definitely required to provide those rigorous methods on designing, implementing, and operating the IoT in the long term. And therefore, we need to join forces. So neither a computer scientist nor an electrical engineer or any other expert can do that on his or her own, but we need to work together. And therefore, we started a new project, a research project called Dependable Internet of Things in Adverse Environments. That's the full title. In 2016, where 10 key researchers, 10 professors from the Graz University of Technology joined their forces across the faculties for electrical engineering and computer science, and we hired 10 PhD students to work on the Internet of Things. And this is how it looks like. The project is divided into 4 sub-projects. First project or first sub-project is dependable wireless communication and localization. The idea here is to explore and research new communication standards like wireless protocols, also wired protocols, for the interaction between the devices, and to also research localization services. So you can maybe imagine if there are IoT devices out there, some of them are statically deployed in a bridge or in some structure, others are mobile. They are deployed in a car, or wearable computing is a very common term nowadays, so you simply wear an embedded device somewhere in your clothes. As you move around, this device is mobile as well, and it might be, in some cases or for some applications, required to know where that device currently is. And so localization services are also very important, and this is covered in sub-project number 1. Then we have sub-project number 2, dependable computing. This is about how should embedded hardware and software look like to make it suitable for the Internet of Things. What can be done in terms of safety, security, real-time, and maintainability? Do we maybe need to change the way in which we have implemented hardware and software in the past? Is there a need for that, or can we simply keep the old style of implementing the devices? And we found out, no, that's not possible, because the static design concept that was used in previous or in the devices so far is not suitable for a flexible Internet of Things. So let's say we have dependable communication and we also have dependable computing. Then, okay, it's nice we have some devices on the table, but they cannot do anything so far. And that's why we have sub-project number 3, dependable composition. These guys deal with the question, how can we connect all those devices? Not in terms of a radio protocol, but in terms of data interpretation. How do we need to provide the data in order to make it readable and usable for other devices? Once we have covered that topic, then we know that our devices can already cooperate somehow. But still, they don't have a clear application, so there's nothing they would do in the end. And therefore, we have sub-project number 4, Dependable Networked Control. These guys covered or addressed the question, if there is a distributed algorithm for something, maybe city management or traffic management, how can we distribute that algorithm across all those devices that are currently available in our city? First of all, we don't know which devices are available because some of them are mobile. They might currently be here. They might currently be in another city because the car that carries that system has moved to another city. And nevertheless, we want to involve we have to involve most of the embedded systems that are currently available to get a lot of data, to distribute a lot of data, and to, in the end, accomplish our goal of a distributed control system. So the question about how do we distribute an application across all those devices is covered in sub-project number 4. And I want to give you some details on sub-project number 2, Dependable Computing, because this is the sub-project I'm leading. It's the one here on the lower right-hand side. Since by 2020, we expect so many devices and the IoT must not fail, our challenge within that sub-project is to provide flexible computing platforms with or for mixed real-time and secure devices. And therefore, we work on operating systems on the one hand and on processor architectures on the other hand. So our idea, in contrast to what has been done so far, is to not only adapt operating systems to the hardware, so that's the common concept, but we also adapt the hardware to the operating systems. And this is something that's very hardly found. So most commonly it's like a software developer receives some hardware platform and he has to cope with that stuff. In case of problems, he needs to find workarounds. In case he finds out that a certain algorithm is hard to implement on the certain hardware, then he also has to find a workaround or convince someone about buying another hardware. It's always the same problem. Our idea is to have reconfigurable computers, so reconfigurable logic, for example in FPGAs, where we can adapt the microcontroller platform that is deployed in our embedded system to the requirements of the software, of the application software, but also to the requirements of the operating system or middleware. So that's the idea. And therefore, we have 2 projects that are not only related to this Dependable IoT project, but also to other automotive and space projects. We are currently designing a brand new operating system for embedded devices and a brand new microcontroller architecture. And this is difficult. First of all, it's a huge effort. Operating systems are very demanding. Processor architectures are also very demanding. And of course, in the end, everything should work fine. And therefore, we also apply some formal techniques. This is mainly done within some cooperations with other universities and industry partners, just to quantify the dependability and real-time capabilities of our systems we build. So it's not just the idea of building something and doing some tests, and after some hours you say, okay, there hasn't been an error, so everything looks fine and it's okay. But we do formal testing on the hardware, so on the logic we have implemented, and also on the software, so on the C code we have implemented, to provide guarantees on the dependability. Question is, where would we use these things? So one day we will have an operating system and we will have some hardware, but it needs to be used somewhere. And connected vehicles, smart and connected vehicles, will be a thing of the future. So everybody's dreaming about autonomous cars. Cars, you simply sit in there, you tell the car where you want to go, the car goes there. You have nothing to do. You can read or sleep or whatever do while the car is driving, and you will safely arrive at your destination. Therefore, more in-car features are required. And in-car features, whatever that might be, require definitely more computational power within the car. Another thing is that automotive suppliers or car manufacturers want to have fewer embedded devices, and that's kind of a contradiction. So on the one hand, there should be more computational power. On the other hand, there should be less devices. How does this fit together? So the integration density of each device has to grow significantly. We have to provide more computational power within fewer devices. And the problem here is that by 2020, and I think now it's 2017, we are already close to those numbers. We expect 100 million lines of codes to be executed on about 400 cores within each car, modern car, a high-end modern car. And of course, those numbers are very hard to control. So 100 million lines of codes, who understands everything that's written there? It's difficult. 400 cores, who synchronizes those cores? And therefore, the questions we tackle is compositional systems of system design. So how can we compose those systems? How can we make it dependable and dynamic in terms of middleware design? And how can we involve reconfigurable hardware, so mainly processors, into our embedded systems? Another thing is that there will be more cross-car services. As soon as cars become independent from the driver, they need to get their information and their instructions from somewhere else. So they need to interact with each other. They have to communicate with each other, and this interaction becomes more and more complex. Expecting 50 billion or even more devices in the IoT by 2020, 250 million of those devices will be cars. That's just a rough guess. Depending on who you ask, the numbers will be slightly different, but most experts agree on those numbers. And therefore, we need flexible cooperation, very dependable communication, and automatic self-organization of the entire network and all the embedded systems in there. And point number 4 is flexible customization and long-term management. Whenever you buy a car, then you have some ideas. So what would I want to have, or what would be the features I'd like to have in my car? And you tell the car manufacturer, and the car manufacturer tells you, yeah, that's possible, that's not possible, but in the end, there will be a lot of different configurations. So if 1,000 people buy the same type of car, there will be 1,000 different configurations of the same type of car. And keeping those configurations dependable is also a challenge, and thus we have several projects going on. I've already shown you 3 of them, so the operating system and the microcontroller architecture and the dependable IoT, but we also have a project called Pro to Future, which is an abbreviation for production of the future, which deals with the question, how can embedded systems be produced to make them suitable for long-term use? One other question that is tackled within that project is, how can embedded systems in the future store data and feed the data back to the manufacturer to make the next iteration of the same embedded device even more dependable? So whenever a device finds out, hey, there's a problem somewhere, it tries to take a log file entry, sends it back to the manufacturer, and the manufacturer knows, because of this and that, a certain problem came up, and in the future we can prevent that problem from showing up by changing something. Yeah? Okay. And how are we going to do this? Within the working group, or within my working group, we are not only tackling application concepts, but mainly we are focusing on operating system concepts, and from those concepts, which is on the research side, we also implement an RTOS kernel, so a real-time operating system kernel, which is mainly done within industry projects. And on the other side, we have academic research on microcontroller concepts like pipelining, caches, and so on, all the stuff, but with a very specific view from a software architect, with the perspective of a software architect. And once we have those concepts, then also within industry projects, we implement the MCU, for example, for the automotive domain and also for some space applications. And what we get is, we get an MCU that is tailored to the operating system and an operating system that is tailored to the MCU. And this cross-tailoring is very beneficial. So in the end, through some design tools and the compiler and the synthesis tool, we receive an FPGA bit stream, which is the logic representation of a microcontroller that is flashed into an FPGA device. And then we also receive a binary of our application software that is also flashed into that device and then executed. Okay, I want to give you some details on the operating system and what we are doing there in detail. So our operating system on the first side is nothing special. It is preemptive, it is multitasking, so it allows tasks to run, sleep, or wait for something like events or resources, so that's pretty normal. We have a system time, we know resource protection, we have events for inter-process communication, we have some centralized IRQ handling. That's nothing special. What is special about that operating system is we already allow partial software updates, so it's not required to update the entire firmware of a device, but we can simply replace some tasks, we can remove them, we can modify them at runtime without shutting down or rebooting the entire system. We have multi-core support, and we have FPGA support, and that's really new. So our operating system supports something like plug and play, but not on the electronics or mainboard level, but within the chip. So up to now, you simply have plug and play by removing a certain extension card from mainboard. You plug in a new one, and in case of hot swapping, it immediately installs some drivers and everything works. But you cannot modify the chips. In this case, we can even modify the logic within the microcontroller, and the operating system is aware of that modification and immediately adapts to the new hardware within the chip. And this is definitely something new. Okay, where do we need that? We have currently a project running where we try this concept in a satellite, not on the main system that controls the satellite. That would be a little bit too dangerous at the current stage of the project, but we have some hardware in that satellite that can be updated from the ground station. We also use that in automotive systems where embedded systems are mainly deployed in testing facilities, and the hardware needs to be updated as well because the customer needs that. And we have an autonomous robot running around below some localization system that can also be updated, which hardware can also be updated for new requirements. And I want to show you why it is so important to talk about compositional systems in general, why it is important to change a system at runtime and what the challenges are. So let's assume we have some software running in our system. The software is composed from tasks. We have a very low priority sensor task. We have a higher priority radio protocol task that communicates with the environment. And we have a motor control task for controlling the motors of a robot. And this task has even higher priority just to make sure that we can control the motors at any time in a very reliable way and avoid hitting obstacles and so on. Of course, the software is not sufficient. Software needs to have some hardware. And the sensor task requires a sensor, of course. The sensor is read out by some analog digital converter. The data is forwarded through some DMA controller into a non-volatile flash memory. The radio task requires a radio transceiver. That's straightforward. And the motor control task requires a motor driver that in the end controls the actuator itself. The sensor task will create a data stream. So once it has started the stream will run for quite some time, transfer data at a certain data rate, but it's nice to not interrupt the stream, or to only interrupt that stream if it's really required. Whereas, again, the radio task needs to send data packets to the radio transceiver, or it needs to receive data packets from the radio receiver in order to communicate. But that's not a stream, that's just single and short packets. The same is true for the motor control task. There are some packets going in both directions just to activate or deactivate a motor, control the number of revolutions per minute, and so on. The big problem in most embedded systems is that the connection between the software and the hardware is done through a shared interconnection bus. So there's only one bus that is responsible for the communication within the embedded system. And that makes things difficult, because as soon as the stream is running, which is something like an exclusive long-term allocation of that interconnection bus, neither the radio task nor the motor task can access their hardware through the same bus. You need to stop the stream first, because it's a shared resource. And if the stream cannot be interrupted in time, then it might happen that either radio communication doesn't work as expected, so some packets are lost, or the motor cannot be deactivated in time and your vehicle simply runs into an obstacle. And that needs to be avoided. And the question is, how can that be avoided? How can we design a system that copes with that problem, and even though we don't know which tasks are even running on the system? Because in the future, you might have embedded systems with one or two tasks, and over time, more and more and more tasks will be installed on the same system. So it's not possible to tailor the tasks manually to each other, but they need to automatically adjust to each other and optimize the entire system automatically. Otherwise, this sharing of this interconnection bus won't work. And at the moment, what you would do, or what you would see as a result, is the following. We have the sensor task that acquires access to the resource, to this interconnection bus, at this point in time. So this bracket indicates that there's a resource allocation. Then it works for some short period of time, and here it sleeps. So the data stream is currently going on, and the data is written into the non-volatile flash memory. At a certain point in time, namely here, the motor task asks the operating system, hey, can I get maybe access to that interconnection bus? And the operating system says, no, sorry, the bus is currently in use, you cannot use it. And that's bad, because now the motor task has to wait for some time, and nobody knows how long this time is. It might be just a few microseconds, it might be seconds. In the worst case, the sensor task never gets aware of the situation and keeps the bus for another hour, and in the meantime, you are running straight into an obstacle. Yeah? But in this example, at that point in time, the sensor task releases the resource, so the operating system assigns it to the motor task, and now the motor task can do something. Yeah? Here it releases the resource again, so the stream can continue. And in this example, it's even worse. So the motor task needs to have access again. This time, the sensor task is even running, so it could release the resource. But before it can actually do that, it is again interrupted by yet another task that has nothing to do with that resource. It's just there. It's just running. And this task prevents our low-priority sensor task from releasing the resource. And that's bad, because now the motor task has to wait even longer. And it's even more likely that, that problems will show up afterwards. So manual system configuration, as I told you, is not possible in systems where you compose the software dynamically at runtime, where you install and remove tasks on demand. And such problems are not new, of course, and those are very difficult and critical problems. In 1997, the Mars Pathfinder mission almost failed due to exactly that problem. And still, there is no real solution to that, even though that's so long ago. And we have a concept that cannot provide a perfect solution for that problem, but at least it makes life easier. And our concept is called dynamic hinting. It supports resource requests, temporarily bounded resource requests, and the idea is to make use of the knowledge of the resource manager that is installed in each and every system to indicate the disturbing influence of certain tasks to those tasks who produce this problem. So the idea is as follows. Our operating system has a resource manager. That's normal. Every operating system, almost every operating system has that. And the resource manager knows about all the lasting resource allocations. So it knows that the sensor task currently has allocated the interconnection bus. And the resource manager knows about all the pending resource requests. So it knows that the motor task wants to access that interconnection bus as well. And in this example, we have two tasks down here. One has high priority, and it's currently running. And another task has low priority. We don't know, maybe it's running, sleeping, waiting for someone, we don't care. But we care for one fact, this task has a resource, indicated by R. So this task has a resource. And now, task number 1 requests exactly that resource from the operating system. And in any operating system you find out there, task number 1 will simply put in waiting mode, indicated here, and it has to wait. It cannot do anything, it simply has to wait. And task number 2 will never ever get aware of its spurious influence on the system. And what we have changed, oops, that was a little bit too much. What we have changed is we have a communication with that task, so we send a so-called hint to task number 2 and tell task number 2, hey, you are blocking another task even though you have much lower priority. Go ahead and do something. And just to make sure that this task receives some processing power, we also increase its priority to high. So this is something also known as priority inheritance. Maybe most of you know about such concepts. But the new thing is that the operating system gives a clear indication about the problem. And now this task is free to handle that problem. Important to know is that due to the high priority, it's definitely running now, so it can do something. It's possible for the task to cope with the situation. And in this case, it releases the resource, which is handed over through the resource manager to task number 1, which in the end returns to running state, and the resource handover took place in time. Of course, we need to specify some temporal boundaries, and the task number 2 needs to respect those boundaries. Therefore, we have contracts and so on. And contract design is also not a very simple thing, but we have concepts that allow us to implement systems that way, so we can make sure that resources are always available within certain temporal boundaries. If you want to know more about that concept, then you will hear more about it tomorrow morning in my workshop. Okay, so what's the difference? This is the picture as you have seen it before, with all those waiting times. With our concepts, waiting gets much shorter, because as soon as there is a resource request of the motor task, the sensor task will be increased in priority, so it cannot be suspended by any other task that might run here, and it releases the resource, so the delay between requesting the resource here and actually receiving the resource is very short, and depending on the implementation, it's even constant, which is very nice for real-time system. And the same happens here. There's a request, there's hint handling, so the resource handover takes place in time. Okay. We have not only implemented that in software, but we can also extend that to another layer and involve the hardware as well. Imagine those two tasks are not running on the same core, but on different cores in a multi-core system. Looks like this. So there's core number 1, there's core N, there's a task 1 running here, and there's a task 1 running on that core. Now this core, I'm too far away from that thing, okay. So this core asks for a resource. The hardware also asks for the resource from the other core, and this is forwarded through the operating system. So this task can release the resource which goes through the operating system and the hardware to another core and to the task. So this concept does not only work in software within a single core, but it also works in multi-core systems with lots of cores. Question is there a hardware out there that supports our concept? And the answer is no, of course not. I mean, neither like Texas Instruments, Intel, Freescale, whatever, they wouldn't implement that because they are not aware of the concept. So we decided to go for our own MCU, and this is called Mozart, like Mozart in Austria, but with an S. It's for multi-core and operating system aware real-time MCU. And this MCU is tailored towards our operating system, so it knows that there is an operating system running, it knows about the requirements of the operating system, and it tries to fulfill or to cover the requirements of the operating system. It's based on a RISC-V architecture because we, to be honest, we were too lazy to implement our own compilers. So we are relying on existing tool chains, but we modify the logic of the microcontroller. So it's optimized for FPGA, so it's a soft core. It has multi-core support. It supports various on-chip peripherals like timers, I/O units, and so on, but that's something you would expect from any microcontroller. The operating system aware features, which are a little bit special, are it supports cross-core time synchronization with a precision of plus minus half the processor frequency. It supports task and priority awareness across the cores. That's what we have seen on the last slides. Most commonly, you have priorities for the tasks, but those priorities are only meaningful within the same core. They have no meaning across core boundaries. Within, or for our system, priorities are meaningful across the entire system, also spanning across cores. We have that resource sharing concept I have shown you. We have a task profiling subsystem where we can measure runtimes of tasks. We have application-specific extensions. I will show you an example on later slides. You have security features, and we allow the dynamic modification of that processor at runtime. And this is something I want to show you in detail. So this is a block diagram of our processor. You don't need to read that. And down here, there's an FPGA, and the FPGA has the dynamic reconfiguration area. So this is the reprogrammable logic area, and within that area we can do whatever we want. We can implement software, logic, and deploy it there, and it will be used. But the question is, how can we update that reconfigurable logic area? And therefore we have implemented some network interface. In this example it's Ethernet, but we also have CAN bus support and FlexRay. And through that interface, we access the reconfiguration unit that is hard-coded into the FPGA and can transfer a new processor version into that dynamic reconfiguration area. So once we find out that our processor has a bug, we resynthesize the entire thing and send it through the network into this FPGA. So we have a new version of the processor. What we can also do is we can keep the processor core as it was before, but only modify a timer, because we found out that our timer had a bug. We can update the timer at runtime, and while doing the update, we do not even have to shut down the processor. So while the processor is executing software, we can modify some of the logic in the FPGA. This is a footprint of a very small system where there's just the configuration update logic. There's no processor at all, so this is why everything is black. So this is just to show you how much of the logic cells is in use for this reconfiguration concept. Everything that is black is not in use, and we could use it for processors, extensions, and so on. So imagine this is an IoT device. Then this concept allows us to have plug and play on chip, since we can update hardware just like we can update software. Okay, apart from that feature, we also support a special type of interrupts. In fact, we do not distinguish any longer between interrupts from the hardware and events from the operating system. It's all the same. In most systems you see out there, you have events from the operating system, but they have always lower priority than hardware interrupts. Hardware interrupts have always the highest priority. This is acceptable in many cases, but sometimes it's like if there's a very low priority task waiting for a high priority interrupt, then whenever that high priority interrupt shows up, the handler will consume processor time that might better be assigned to a high priority task. And that cannot be done with regular processor architectures because they handle interrupts different from operating system events. Actually, they don't know anything about events, but the operating system does that. In our concept, we have a unified approach where events from the OS and interrupts from the processor are handled in exactly the same way, so they can also respect the priorities that were assigned by the software developer during development time. Another thing is, whenever you have multitasking, then you need stacks. For each and every single task, you need a stack. And the size of the stack is very hard to find out. So how big would you choose a stack? That's the typical question a software engineer has to answer. And most commonly, the answer is, I don't know. I will simply assign 1 megabyte. That should be enough. The result is that in case it's not enough, the system will simply fail. In case it is too much, then you will waste memory. And this is something we wanted to avoid. So we have stack blocks, which is like a linked list of memory blocks. And whenever a task requires some more stack, the processor automatically assigns more stack to that task. And this is totally transparent. So the task does not need to know anything about our concept. It simply asks for more stack and it will receive more stack. Unless the entire memory is full, then of course we will also run out of resources and the system will fail. But up to that certain point, it's no longer required to clearly define or statically define the stack size right from the beginning. And the last thing is secure MPU. We have implemented a memory protection unit that is a little bit different from most memory protection units you might know, because in our case, it does not only protect arbitrary memory blocks, but this MPU can also protect resources. So in case you have a task that wants to access a timer, and the timer is implemented as an on-chip peripheral, then you can use our MPU to protect that timer from unauthorized use. So no other task can access that timer and mess up the configuration in there. And in total, that helps because if you implement a system nowadays, you don't care too much about security because you think, I know what's going on there, I know which tasks are running, so I don't need to protect on-chip peripherals. But in the future, when new tasks will be installed at runtime, you never know what others might do in the future, so it's a good advice to protect yourself from others by protecting the resources you're using. Okay. And you might wonder, how do we keep all the stuff consistent? So we have the OS on the one side, we have the MCU on the other side. It has to fit together. All the memory addresses, all the logic, everything has to fit. And of course, you can do that manually, but that's very error prone and it's very time consuming, and we don't want to spend so much on that because we want to focus on our research. And therefore, we have implemented or started the so-called AutoIOH. Now it doesn't work any longer. The so-called AutoIOH support tool that receives a system model, and from that system model it automatically creates a software stubs, so you can implement the functionality of the software later on. It creates processor stubs for VHDL or Verilog, and it also creates, but that's very experimental at the moment, a circuit layout for your embedded system. And in the end, it makes sure that those three parts fit together. So you receive a PCB, you receive the bit stream for the processor and the firmware for the software, and everything fits together. And this is an example we have implemented for a company. The actual idea is to implement some motor control unit, but that's you cannot see much in that motor control unit. That's why we extended it a little bit. In the upper right corner, you can see a PCB. There's an FPGA board with some extension wings, I would call it wings. And the PCBs for those wings carry RGB LEDs. So if you turn the thing around, you can see it from that side. So there are some LEDs that can be controlled, RGB LEDs. And as soon as this entire thing rotates, it looks like this. So you can display images. And the system design is made, as I said before, we have the system designer, the AutoIOH creates software and processor, we receive bitstream, and then we deploy it. And if we find out that something in here doesn't work as expected, we can redesign the hardware and the software, generate new firmware and bitstreams, and deploy it again while the thing is running. And that's the cool thing. While it displays some images, we can update the hardware and the software. And this is how it's done. We have a processor core running our operating system. We have an interconnection bus that connects the core to a graphics accelerator that was implemented by ourselves. So this is the device that activates and deactivates the RGB LEDs in time so that in the end you can see an image. And at that bus we have open ports. So implemented in the FPGA, we have some logic that allows us to attach new logic. So whenever we find out that our graphics accelerator has a problem, we simply add a new graphics accelerator, so the old one is no longer in use. We can reuse the logic cells for other things in the future. Instead, we use this graphics accelerator to access the LEDs on our extension boards. And of course, those open ports could also be used to add control logic or measurement logic, crypto units, DSP units, and so on. We're still at the beginning of that concept, so it's more experimental, but we can already see that it works. And okay, of course, we could also add another core. This is something we are currently working on. It still doesn't work as expected, but the idea is in future to also add new cores to the system. And as I said, we have this secure I/O concept where we can protect all those on-chip peripherals from tasks that are not authorized to use them. Okay, so yeah, this is my team working on it. And those are some examples. Let's see. On the left, though it's hard for you to distinguish, but the left video shows that the image we're displaying gets updated. And this is because the software does the update. In the right video, it looks almost the same. The image changes as well. But in the right video, the hardware is updated at runtime. And as you can see, there's no flickering, there's no strange rotating of the image when I play those videos, because our concepts allows us to do the update within certain time boundaries, so you cannot see that the update actually takes place. Those black things you can see are because of the camera. In the real image, they are not there. So this is just like a regular image update as you can have it in any embedded system, nothing special. The image is just updated, but here the hardware is updated. Whenever the image changes, we have some new hardware component displaying that image. This is a tower in Graz. Now there's another update. This is the Graz Lion. And you can also see there are some red things. This is just for synchronizing. This is the Macedonian flag because we have a Macedonian PhD that does the work. And you can see those red LEDs. This is for synchronizing the rotation speed, or synchronizing to the rotation speed. And if everything slows down or speeds up, then of course the image will adapt to the new number of revolutions per minute. Okay, those are some still images, so you can see them better. And the concepts have been applied not only in this experimental setup, but also in some industry projects. So for example, there was a project with BMW where we did some human interface device with our concept. Then I already told you about the satellite project. Then there is some automotive testing system at a big automotive supplier in Graz that also relies on our concept. So here you can see a PCB with extension cards, and here we have plug and play, not within the chip, but on the main board, but it's treated in almost the same way. Okay, if you are interested in those topics or in the Internet of Things in general, if you want to submit maybe your own research papers, then I can invite you to submit them to the 13th International Symposium on Industrial Embedded Systems, which has a co-located workshop or symposium on the Dependable Internet of Things project. It takes place in June 2018. I will also provide some call for papers out there, and this is maybe also a nice opportunity to visit beautiful Graz, which is a city in southeast Austria, founded in the 6th century. It has 2 UNESCO World Heritage Sites. It has 4 universities, so it's a student city with about 45,000 students, 15,000 of them at Graz University of Technology. And we have a lot of automotive industry in Graz, so maybe that's interesting for you. Thank you for your attention, and I'm open for questions. Sorry?
Talking about billions of devices, price matters of FPGAs, price of FPGA node.
The price, okay, yeah.
Yeah, so do you think in the future the manufacturers would be able to manufacture at a lower price, lower cost?
We think so. So the prices of FPGAs are dropping significantly at the moment. And since domains like the automotive domain is aggressively asking for FPGA solutions, we also think that this has another impact on the pricing. Apart from that, most of the systems we are doing are not meant for huge quantities of devices, but only for very specific applications where pricing is relevant, of course, but not that relevant. So we are not talking about millions of devices with those chips, but very customized concepts for automotive testing, for example, satellites and so on. And there it's definitely acceptable.
So the reconfigurable architecture you have, is it the operating system, is it like making use of the reconfiguration, or is it like the operating system running on its own and the architecture? So when in real time you say like the architecture is reconfigured.
Mm-hmm.
So the OS is going to make use of those changes and adapt?
Right. So the operating system is aware of the fact that the processor could change at runtime. And whenever that happens, then the processor notifies the operating system, hey, there will be some change in a certain component, let's say in a timer. So the operating system knows that no task is allowed to use that timer during the update process. Then the update process takes place. The hardware notifies the operating system again and tells the OS, it's done, you can use it again. Maybe a new driver has to be used then because of some modified functionality, but then the OS can allow other tasks to use that component again. So the OS has to be aware of that fact, and the other way around, the processor has to be aware of the fact that there's an operating system running, otherwise it cannot tell the software to not use that component while the update is going on.
And the architecture's instruction set is still fixed, right? So it's not changed.
We have not modified so we have not changed the instruction, but we have added some new instructions. So the compiler, the standard compiler for the RISC-V still works, but if you want to have all the features, then you need to have a slightly modified compiler that introduces new instructions.
So how does it work in real time? So if we can, the compiler works in real time, make use of the changes
At runtime, we are not making changes to the instruction set. So as long as you don't change the core itself, but only some extension like this graphics accelerator, then this doesn't affect the instruction set at all. If you want to change the instruction set at runtime for whatever reason, then you would have to replace the entire core, which is possible in general, but this will probably violate some real-time boundaries. Yeah. It's not meant for, even though you could change the core, it's more or less meant for on-chip peripherals. Yeah. Okay, there are no other questions then. Thank you again.
To felicitate Professor Marcel Baunach, I would like to invite Senior Professor N.D. Kodikara.